PowerPoint here. So I will talk about pump and VFDs 101, some energy savings with some speed control versus valve control, and some basic troubleshooting. I actually brought a demo, and we'll show our participants here how to use the speed control live through a potentiometer, and also be able to do some basic troubleshooting and commissioning towards the end of our presentation. So without further ado, let me share the slideshow here, and let's begin. So thanks for having me, Ricky, and the AZ Water Committee team. This is Pump and VFD 101. So let's start. All right. So let's begin with energy savings. That's why I was initially brought on here. We want to talk about full voltage, reduced voltage starters across the line, and variable speed. So what are the disadvantages of full voltage starting? I do have a graph to show this. You have a inrush going into your motor, and it's about 600% of the full load operating rating. This creates mechanical stresses, electrical stresses, and let me see. Why would we do motor starting? Hold on a second here, and if you can, please mute your microphones to reduce some of the interruptions here, but feel free to send questions towards the end. Reduced voltage starting will be shown in a second here, and you know, I do have the noise here on the slide, so hopefully I can mitigate that at some point. So the reduced voltage starters here, why would we reduce the voltage? Is through, again, as I mentioned, reduce electrical stresses, mechanical stresses, increase the motor life. And I really want to go to the graph here. So across the line creates a 2,400 inrush initially, and then once we go into a reduced voltage starting, we can see that is heavily reduced to 1,500 here. So when we go through the soft start to coasting to stopping, we can also use VFDs or soft start to reduce the water hammer. So by extending your stop time, do dynamic braking, and also help protect your mechanical motor applications. Here are some basics here. Here's the advantages of across the line starters, inexpensive, readily available. And then you go to your better and your best options, which is the reduced voltage starting and your variable speed control, which we will discuss how we can take advantage of by changing the speed. So let's start on flow control. How do you achieve flow control traditionally? I mean, valves, dampers, vanes, diffusers. We'll go through that as how that affects the system head pressure and efficiency of your system. Recirculating systems are another way of achieving this. All these restricted flows and devices increase the heat, the friction, create wear on your equipment, and require maintenance. So this is a great analogy, as if you were pushing your pedal on the accelerator, and to control the speed of your car, you would just hit the brakes. So obviously we want to avoid that. With an adjustable frequency drive, we can control by actually reducing the speed and achieving flow and pressure and energy savings. It is a low cost to retrofit. It's more a deal of soft starting and stopping. I did talk about the water head that we can also reduce by higher efficiency, noise reduction, and we can also simplify the operational maintenance. Okay, for starters, let's go with a VFD. How does a VFD work? You have your three-phase power going into the converter section, onto a DC bus, and then through IGBTs, you create a pulse width modulated signal that recreates a power wave going into the motor. And this pulse width modulated signal will have a frequency here.
What's an IGBT?
Insulated gate bipolar transistors. So these are solid state devices that can help pulse back onto the motor and recreate an AC power wave. So this is important just because we have a VFD. This has to go directly onto your inverter-rated motor. Otherwise, you can have issues if you try and apply this into a larger system. So make sure we're going directly into the motor, the compressor, the fan, not into a system that has PLCs or other components, for example. But again, let's go through a few things here. How to achieve energy savings with a pulse width modulated wave. So the pulse width modulated wave, the flow and the hertz, GPM, RPM are proportional. Your head is a square and your power is a cube. So these are the affinity laws. This is most common in variable torque loads. We will discuss variable torque versus constant torque in a few. But theoretically, if you can achieve half speed, overcome 4 times the pressure, 3 times the energy savings. And let's think about that a little bit. So the fan or pump energy input here, you see the power consumption of using a valve or a damper control versus an adjustable frequency drive. It is a big difference. I have a specific example on this as well. So if you're looking here, your static head versus your friction head and your system curve, let's compare that 1-to-1. So here are an examples of a few pump curves and the flow rate that you need to go to be able to overcome the system flow. So if you go with a full speed at a higher head, here's your curve here, your system curve and your pump curve. But if, let's say, we require reduced speed and we use a valve, we still have a high head of pressure to overcome, and then compare that to a head using a variable frequency drive. So your head significantly was reduced by you just reducing the speed and a VFD. So here are the 2 graphs for comparison. Obviously, there's a big difference here. You used a different pump curve to achieve this, and all that extra head that was not used is the energy savings. So here's a few different examples. Obviously, anytime you're using a valve or vane, you go into the higher head curves, and then with adjustable flow is the most efficient operation here. And this is a good example just because a lot of times when we're designing pumps, VFDs, we do need some redundancy. So what I'm going to ask here is that we can use both methods. So let's think about this a little bit. So for this system, when we have a 100 horsepower motor, a pump, and we're using a valve to reduce the flow in the system, we're actually adding some head here. So we're adding head from the higher horsepower motor, we're adding head from the additional piping, the valve turn down. It requires a 90 horsepower to overcome that system flow. Now let's compare that to maybe using an adjustable frequency drive. You reduce the piping, you reduce the horsepower of the machine, and then obviously you do not have the loss that you had through the turn down on the valve. That is significant. You go from 100 horsepower to 75 horsepower. So what I mentioned initially is because we do have many critical systems, we can use this as redundancy. So you can have a PLC control using both methods. You can have your adjustable frequency flow and just reduce the valve for energy savings. And then you can have your emergency or bypass operation with valve control. So good thought there. Let's continue on here. Most fans, pumps do operate at partial loads. So I will go into this further down the line with slides, but a critical thing we need to think about here is let's look at our pump curve and let's analyze what the minimum speed should be applied onto your VFD for safety and to avoid any issues with your system. So now that I'm focusing on energy savings, let's go back to the slide here. This is a good example. So on a 100 horsepower application, operating at 60% flow with roughly 6 cents kW hour, 5,000 hours per year. If you're just using a damper valve, this would be your consumption at a year, 20,000 versus using adjustable frequency drive. There's instant energy savings here on just a simple 100 horsepower application as an example. Obviously, there are energy savings achieved through vanes and dampers, but not as near as how much you could achieve with a VFD. All right, so now that we've gone through the basics of energy savings, let's go through some of the troubleshooting and commissioner basics. So this is going to be a fun one. I do have a live demo again that I will switch my cameras here and show you how to operate. And if you have some questions on programming and parameters, we can definitely look into that as well. So troubleshooting, before you go out and try and troubleshoot a VFD or find what problem you may have on your system, it is important that you know your VFD manufacturer's phone number, email, and that you have your manuals in hand. A lot of the time, the manuals can give you the basics so that you can yourself be able to troubleshoot the VFD or motor and machine. So the basics here is gather information. The most important thing I would say, I mean, obviously other than the safety inspection and lockout tagout procedures, is to review your installation. So have your pump submittal, have your VFD submittal, maybe your control sequence of operation. Program your drive based off the motor nameplate. This is critical. Whatever values from your motor nameplate you program onto the VFD are going to be the basics in which all the safeties and algorithms are calculated onto the drive. Bump your motor. Make sure that your motor and VFD are rotating the correct direction on both VFD mode and bypass mode. We can review that further and how you can adjust that. You can test your operation, send the manuals to your operators. One of the important things here is you should have a backup of properly operating the VFD, whether it's through your computer or an additional keypad that you can save and have as a backup. And then submit your paperwork for what programming you did, the backup operation, and also if you had a certification, be able to submit that online. So here are an example. We were going to go discuss about constant torque loads and variable torque loads. So what does constant torque mean? And if you've worked with positive displacement pumps, this is a very common application. You have constant torque with changing speed. So what you do here is 150% of your torque rating can be achieved for 1 minute every 10 minutes. Let's compare that to a variable torque application. This would be an application where you have 110% of torque for 1 minute every 10 minutes. And this is an important graph to look at because you can use a constant torque VFD on a variable torque application, but not the other way around. And there's more benefits on constant torque, such as higher heat rating and being able to withstand more in a longer lifespan than a variable torque VFD. So when in doubt, please always try and apply the constant torque formula. Moving forward, let's talk about some filtration here. The AZ Water Committee wanted me to focus on what filters, what types do we have, and input and output filtration when applying a VFD on the system. So there's going to be two types of filters that we talk about here. Input filters are going to be for the line harmonics. Output filter are going to be your lengths from your VFD to the motor, and they're both very important considerations when designing and installing your motor pump VFD application. So what are harmonics? We talked about the three-phase power going into the converter section and being chopped up by diodes into a DC bus. All that switching from AC to DC creates power system distortions. So as you can see here, this power wave is not a smooth wave. All this distorted AC waves will potentially damage your electrical system, will give you some faults. They can also overheat equipment. And here's a good rule. These are the most common harmonic filtration methods on the input. And sorry if you can, I'll mute please, that would be great. So some common filters here are the inductive reactors for the lower horsepower. If you have some budget concerns, passive filters are a great method. And then you also have some other technologies such as 18 pulse converters on the higher horsepower range, active harmonic correction, and there's also matrix technologies which also can help achieve harmonic filtration. And all these harmonic filtration methods will give you different results. Inductive reactors will have a THD, total harmonic distortion, of 30% roughly. Passive filters can have either 10 or 5%, and then active harmonic correction, 18 poles, will have less than 5% total harmonic distortion. And they all have their advantages and disadvantages. I mean, 18 poles converters could have some less performance with phase imbalances in the power system, whereas maybe active harmonics does not. But let's say 18 pulse converters actually can achieve total harmonic correction at partial horsepowers, whereas maybe active harmonic correction might not be able to achieve that at 50% motor speed. So there's pros and cons, obviously size, budget, application. It is important that you apply the correct harmonic application for your needs. And then when in doubt, your drives, industry has standardized on either DC link chokes or line reactors that will reduce that power distortion from 80 to 110% down to 30%. And in order to analyze this, you should follow procedures from IEEE 519. All right, we talked about the various different drive technologies here that can help with harmonic correction at the input of the drive. Let's talk about the pulse width modulated wave. The pulse, so the recreated power wave that goes from your VFD to the motor. This also might require some special filtration here, and these are some of the recommendations that we have. So for a 3% output reactor, you can have a good performance between 100 and 300 feet. GVDT filter when you go at 300 to 1,000 feet, and then a sine wave filter above 1,000 feet. So if you have a well application, you might run into sine wave filters, and you could also consider being able to properly size your system so that you can overcome losses. All right, so we have gone through input and output filtration methods here. Let's talk about the installation and the commissioning. So most importantly, before opening the drive, let's make sure that you follow lockout, tagout procedures, arc flash safeties, and before opening the cover. And make sure that you have disconnected power from your panel board or MCC before touching any of the high voltage. One of the basics here is the grounding. Make sure that you have ground your motor onto the drive. Follow the instructions from your manufacturer installation manual. Shielded VFD cable is recommended. And we did talk about motor line lengths. So if you have, let's say, an inverter duty motor, inverter duty cable, you have more leniency as to not necessarily having to have a long line length filter on the outputs. And all that pulse width modulated waves can be smoothened out to be able to achieve longer lasting machines. The basics here is whenever you start a drive, it should have a startup wizard. And the startup wizard is a basic 19 parameter here as I show, where you have to pass the motor nameplate data onto your VFD. So most importantly is make sure that your values transcribed here come from the motor nameplate. This is critical. You might see many nameplates on different portions of the system, but make sure that the motor on your pump is the one where you're programming into the drive. So let's move on forward here. Once you have programmed the correct parameters, be able to bump your motor. The right rotation is critical because you can have scenarios where the drive is running correctly, but not the bypass, inversely bypass and not the drive. They could be both running in reverse, but to achieve the correct rotation, make sure your input lines are wired appropriately, output from the VFD to the contactor and from the contactor to the motor. An example here that I'm going to show in a second is being able to use a potentiometer or a two-speed signal to be able to control your VFD speed. And when you're going through the design procedures, make sure that you have your terminals in the correct locations on the drive. And we'll discuss that further, but let's talk briefly about the programming and the commissioning. One of the most important aspects here is to change your minimum frequency. Now, if you have a pump application, please do not change this to 20 hertz. This is mostly for a fan application. It is important that you look at your pump curve, communicate with your operator, and if the minimum is, let's say, 60%, that you go at maybe 36 or 40 hertz and have that as your absolute minimum every time your VFD starts. And it is a simple way to update and change this on your VFD. Here's some examples of how you would do it if you were to go on the parameters with the drive. And then again, being able to upload the data from your VFD to have as backup to be able to use for, let's say, an emergency or secondary storage keypad. You can use that simply. It's a little bit more complex. You got to go through more steps, but you can also do this through connecting your computer directly onto the VFD. So here are some of the key takeaways. I mean, I do want to answer your questions, and I do want to go through the demo with you, maybe do some programming live so that we can talk about what you want to learn about the drives. But the adjustable frequency drive benefits are reducing the energy consumption, longer mechanical life, be able to improve the maintenance, and then you have some of the controls, your Profibus, your Profinet, you can integrate, you can eliminate surges, and then you can also improve your power factor. So again, that is it. Before I go to the demo, I kind of want to go back to the group here, go more into maybe a discussion and questions. And before we start going on to a VFD demonstration with the group. So let me stop the presentation, and how can I help the team here before we go live onto the VFD? And then feel free to questions, send them in the chat, or also you can unmute yourself to help with some of the questions that we may have here.
Hello, this is George with Darkcore. I have a question on the VFD shielded cable.
Go ahead.
And is that recommended every time, or is there a different way of fighting the DVDT issues on the output of the drive without that shielded cable?
So there's different methods we can use here. Actually, let me pull out a table here that can help with that. There are different methods to achieve long line length applications. And there's not a single solution here that we can just focus on. But I do have this handy here. All right. Line lengths. Just give me a few seconds. And I'm just pulling out our recommendations here that we've seen in the field that might be applied best when dealing with long line lengths. All right. So here is a rule of thumb. Let me see if I can share this application with the team here. Share contents. Can everybody see the example configuration that we have for long line length applications?
Yes, I see it. Thank you.
So obviously, when you have inverter duty cable, you have more of an allowance to be able to go longer from VFD to motor without having to add reactors, DVDT filters, or sine wave on the output. But if you do have an inverter duty cable, inverter duty motor, you can go up to 300 feet without having to add an additional component on the output of the drive. So thanks for that. Let me see if there's any other questions. And I did go through some of the basics. If no other questions, we can definitely go into a live demonstration of a VFD, maybe go through some parameters here that you might have suggested. And then let's see what else I can go through here. I wanted to know if there is any further discussion with regards to, before we go on to the demo, maybe a harmonic filtration on the input, the pulse width modulation from the output of the drive, and the line length considerations, energy efficiency, valve control, or speed control. All right. So let's move on to a VFD demo then. We do have this available online. So whenever you do need to troubleshoot, you can go through a system in which you can apply whatever parameters you have or questions and be able to do so electronically prior to going. But it is a very straightforward operation. Your VFD here can be operated a few different ways. It can be operated through hand control, remote control through IOs, or control through your PLC system directly onto the VFD. So a Profibus, Ethernet IP. Make sure you do have the right card selected when designing and installed when connecting onto the systems. Your VFDs do have some excellent capabilities for PLC control. They can also do some multi-motor applications, and there's just a lot you can do with a VFD. So let me see here. I think we just got a message, but hopefully you can see the picture here. And let's start the machine on local. So this is going to be straightforward. We're going to go through the local control. And what that means is we can control the drive directly from the VFD. So when doing that, it is a very simple procedure. Once we properly program from your VFD motor nameplate, again, it's important that you use the correct values. Your VFD will control the speed of your machine. So there's a lot of neat benefits here. You have your safe torque half, you have your IOs, so you can add pilot lights, switches, buttons, extra safeties. You can add a bypass. The VFD that I show here does not have a bypass, but you can do a 3-contactor bypass, or you can do a soft start bypass, or you can do a redundant VFD bypass for critical applications. So you can have one drive as master, secondary drive as slave, and be able to operate your system in critical applications when one were to fail and have the other take over. So right now we're controlling the VFD and the motor through keyback control. We can adjust the speed by going up and down the arrow. And let's see if we can go back here to the menu. Back. And change this to remote control. So to make any changes, let's stop the machine. Go back to remote control. And now you see that the IOs, if you have the screen here oversized, you can control through DI1 and then use the analog potentiometers, and that could be a 0 to 10 volt signal, 4 to 20 milliamp signal, controlling the speed of your pump. So for here, you have digital input 1 as your start command. In order to start, you do have to reset the start signal. So for now, let's reset the start. make sure we are on remote control and start the machine. So let's go back to confirm that we have local, remote, back, and reset. And actually, it did send the signal to start, but what I actually forgot was to do the analog and be able to raise the speed of the machine. So let's say here's the 0 to 10 volts. As I increase the potentiometer, you're going to see the motor adjust the speed, and that can be replicated by using a, again, 0 to 10 or 4 to 20 milliamp signal. And be able to adjust the speed. So some of the neat things here is the switching frequency. If your noise on the drive is bothersome, you can change the switching frequency. And what that means is the number of those IGBT pulses on the output, the frequency of that can be reduced or increased to change the frequency. Now, keep in mind that when you do switching frequency changes, you can, and this is a great example in the field. If you have, let's say, a dog or a cat, they might be more sensitive to those changes, as so those are much higher frequencies. And instead of fixing the VFD noise, you might have some animal noise in the background. But that is a joke. Let's move on to the VFD. And again, live drive through remote signal, adjusting the speed. You do have your LCD displays here, so you can monitor the frequency, monitor the current, and you have a multi-monitoring application from the drive itself, where you can look at parameters. And let's see if we can review some of these parameters. So let's go to the menu here. So hold on a second. Now that we've gone back and reset, we are on the monitor menu. So here, and it's difficult. Hopefully you can zoom in and see some of the features here. Maybe I can go back to the slideshow, but you have many ways to monitor your VFD. When you have a drive, you have a 3-phase power going in, 3-phase power going out. Your VFD is sensing all that voltage, current. It can gather that data. So if you have a PLC or control system, you are actually gathering all those values, and you can use that, again, for an Excel spreadsheet, look at how your drive is performing. If it faults, be able to analyze a fault correctly. The drives do have overcurrent, over amperage, maybe a loss of a belt. They do have all these extra features on the drive itself. And all that monitoring can be either stored at the drive or downloaded if you have it connected directly onto your PLC control network. So again, these are the parameter menus. Let's go back here to the next menu on faults. So we have monitor here, we have parameters, and then we have faults. And then I did loosen the screws here so that we can also look at the I/O and terminal on the drive itself. So this is a drive machine. Obviously, try to avoid touching any of the high power. We're just going to focus on the low voltage, and by high power I mean the 230 volt or 120 coming from your outlet. So now that we have the fault menu here, you can see all the stored faults from the drive, your active faults. You can reset your faults. These are all features that we have here. You can have much data that actually can be stored and achieved. So that's the basic of it. But let's open the drive cover and let's look at some of the IOs. As you can see here, what I was going to try and do today is connect my drive into the computer and be able to go through the menus with you. Unfortunately, it seems like as soon as I connect my computer to the drive, I do lose the Wi-Fi capability, so I wouldn't be able to be with you right now. But right now, you can see that all the I/O terminals here are on the left of the drive, and this is where you would connect all your buttons, your relays, your switches. You have also a lot of expansion boards on the bottom that you can use to add additional I/Os onto the drive. So again, this is a demo. You see a lot of the connections here going back onto the panel that we have here for demonstration. Your I/O Ethernet here, and right now, since we have the drive in I/O remote control, I can actually remove the keypad and still have our machine continue working because all the control is being done remote. So as soon as I remove the keypad, you see that there is an additional Ethernet port right there onto the drive. So for this specific drive, this I/O port is actually helpful to be able to upgrade firmware and be able to connect onto your computer and change some programming. Maybe you want to do for certain drives a low temperature that could require reprogramming. And again, this keypad is where you would upload all your data, save as a backup so that you have a system backup. Or, like I'm showing here below, using the Ethernet or connect directly onto the drive and save the parameters and the programming onto your computer. So let's see if I can somehow put the keypad back in here. If not, we can just proceed without it. But most importantly, when I'm trying to put this back in there, if you guys can think of questions or a scenario where you'd want to go through, we can definitely go through that. All right, here we go. And then again, the speed control is very straightforward. We can actually use also a valve. So let's say if you do have some valve control parameters, you can program through either your PLC or your drive, open valve, start drive, close valve, safety, and shut down at the drive. So there's obviously many different ways we can address programming in the field. It's a very neat application because of the flexibility. We have so many ways we can customize to your needs. And again, VFD does have some PLC multi-motor capabilities and a lot of extra benefits here that we can use without having to go into a full-blown system. So let's see if I can reduce the speed here. I mean, since a lot of this, I think, is switching frequency noise, it might take a while for the drive to either slow down. Oh, one of the good things that I haven't mentioned is the safe torque off feature. So sometimes you might have an application, let's say a positive displacement pump, where you want constant torque no matter what, even if your drive is somehow shut down, you do want that constant torque. You can have those capabilities with the safe torque off feature, where if anything were to happen to the drive, you can maintain torque even if your drive is faulted or has 0 hertz on it. So let me see if there's anything I can think of the top of my head, but for now, let me see if I can stop the drive. It'll take a while for the drive to not make all this switching frequency noise going back to us, but now that I've gone through some of the basic features, basic programming, some basic troubleshooting, and recommendations from the field, I do want to see if the group here, the Arizona Water Committee, or any of you guys have any other suggestions, questions, or if there's anything else that you would like me to cover. I think we still have some pretty good time, a few minutes, so please let me know what else that you'd like to learn about VFDs. I could also send some suggestions to the team here. Let me see. Yeah, I would be happy to share the slides with the Arizona Water Committee. So definitely will do. One of the topics that seem to be emerging in our industry is harmonics. Would you guys like me to touch more on harmonics or IEEE 519 recommendations for being able to meet that in a system? We can also go through that briefly, discuss it. Most recommendations are 5% distortion at the point of common coupling. So what that means is the point where utility connects with the user. It's important to note that IEEE 519 is not intended to be applied at the MCC level, at the panel board level. You may want to do so because sometimes adding that extra level of protection, let's say you have a critical system such as a hospital with very sensitive equipment, an MRI machine, it could be a good application to have a strong filtration there at that point, whether it's at the panel board level or MCC level. And obviously there's a lot of methods we can achieve there. So some of the creative ways we can do so is if you have multiple small horsepower drives, we can add a filter at the MCC, or if you have, let's say, just a few large drives that are operating at full speed, passive filter is always a good solution for that. So I know harmonics is do default to that because it's one of my most interesting, fascinating things that we can see from the drive causing distortions onto a system. Keep in mind that when you might have an application where you have a large facility yourself with large horsepower machines, you may be perfectly fine in your building, but the level of distortions that you achieve just because of the kW or the current distortion that you should be mitigating could also spill over onto other smaller buildings, or if you have a transformer going down that single line diagram onto your neighbors. So if there's anything else other than harmonics that we can discuss, I know there's some great bypass applications. We talked about the ways you can bypass a VFD. That's through an across-the-line starter. You can bypass through a reduced voltage starter, and you can bypass also with a redundant drive application. So other things that the team can think of here. I know we have a few minutes left. Can definitely share the slides, can definitely go through some more applications, but the most important thing here is VFDs have become very user-friendly. Most of the drive technologies nowadays come with a startup wizard, and the most basic requirement that will get you 90% of the road is being able to program that motor nameplate onto your VFD startup wizard. It is very intuitive. There's a lot of backup, such as manuals, in-person training that can help with that. But the I/O procedures integrating onto a PLC or control system is essentially universal across drives. And then obviously, again, going back to the harmonic technologies, it's important that we use the right harmonic filter for the right application. We do not want to provide a solution that requires maybe more than 60 hertz, which you can do with the drive. Your pulse width modulated signal can go above 60 hertz as long as you're below the motor FLA, full load amps. And you can actually, with certain drive technologies, you can do that. Maybe with some other drives technologies, you might not be able to do that, or the harmonic correction performance might look different at those levels. So those are very good considerations to have at the top of your head. Always have your conversation with your VFD manufacturer, be able to talk about all the horsepower that you are adding into the system, and be able to devise the best method of filtration at the input. And obviously, if you have inverter duty cable, inverter duty model, you do have some good leverage on how long the line length can be from the VFD onto the motor. And there's always field solutions such as output line reactors, GVDT filters, and sine wave filters that can help achieve that smooth wave operation and clean power going from your VFD onto your pump machine. So I essentially covered all the topics that the team wanted me to go through here. Happy to share the slides with the group. And if you have any questions, feel free to reach out to me. We can go through some demonstrations. We can go through some ways we can mitigate through different drive technologies, and happy to answer anything else if you think of things outside of what we have here. But let me see, I did have another question on the chat. Yes, we do have some technical specifications to help with the range of voltages, the NEMA ratings, and that is a good question. NEMA ratings is important. We do have a NEMA 3R solution. We have AC NEMA 4X. We do have ways that we can do an fan filtered NEMA 4 applications. There's also explosion-proof drives that we can offer. There's a lot of flexibility. We do have our own manufacturing in Watertown, Wisconsin, and we have many interesting applications, anything from your standard NEMA 1 to NEMA 12 to a complex explosion-proof class A, B, and C. So definitely, yes, reach out. The best way, let me see here if I can answer you, Jason. If you want to reach out to some of the offering that we have, the easiest way to go through our website is through this message I just sent over to the team here. So obviously, some of these larger horsepowers, low voltage, medium voltage, you should be able to find at this link I just shared through the team's chat. We do have, again, technical specifications for all the different drive offerings, 230s. Some of the neat ones actually that are here online. You can see that this is not a three-phase VFD. I'm connecting this to my home outlet and I'm going through the live demonstration. So you can go through single to three-phase applications. Those are very neat solutions when you have 120 or 230 single. There are, however, some limitations. I believe the 120 volt to three-phase are very limited in horsepower range. But as long as you have a 230 volt single to three-phase, you can actually have some great solutions if that is all you have in your system, without having to redo your single line diagram. And obviously the input protections, the UL rating, the NEMA rating is all according to that. The caveat to that is you cannot have a bypass when you have single to three-phase applications, because the VFD is what's using that single phase and replicating that into a three-phase going back onto your machine. Again, and when you are going through single to three-phase applications, there's a specific oversizing and potential capacitors that you may need to use to be able to have the application to work. So that is if you're using that in the field. If you're getting it as a package solution, that can also be offered as a one drive in a box, meeting all rating required for those types of neat applications. So thanks for the question there. That brought me to some of the cool offerings that you can do with a drive that are usually not thought of. Anything else that the team here can chat, let me know. I would be happy to answer. But definitely do appreciate the Arizona Water Committee having me here. We talked about going through a live demo, having it more direct to the group as to what you would like to hear from drives, and just very happy got the opportunity to speak to the AC Water Committee. So if no other questions, I do want to send this back to the AC Water Committee team. Really appreciate your time. Encourage you to reach out to me, and happy to answer all your VFD questions. Thanks again, guys.
Hey, Nick, can you flip to the last slide?
Will do. Let me share the last slide here because we do have the program for the next month. So let me open that up real quick.
I'm Ricky Holston, the webmaster with the Arizona Water Distribution Committee. We want to thank you guys for attending. We do these monthly now, more or less. Next month is do's and don'ts of tank maintenance by Blue Locker. They're tank diving inspection services. So if you're interested in that, the event will be on the website that you'll be able to log in here. It'll probably be a few days. It's not in there right now, but and then we encourage you to check back every month. We're adding stuff for the next months, and we're going to keep doing this as long as social distancing and webinars are needed to get our information out there about the education. So we appreciate you coming again. Thank you, Nick at Eaton. That was a wealth of knowledge. My head is spinning. That was a lot more about VFDs than I anticipated, and it shows me that how much more I need to learn. So I appreciate it again. And, you know, Nick, I'm sure that you would appreciate, you know, if you have questions or whatever, you guys can feel free to reach out to Nick. He'd be a great contact and resource going forward. Or at least I can get you the right people if he's not. So once again, thanks a lot, and we'll see you next month.